What I want to talk about in this model is about terminating system, learning how we can capture terminating systems in a simulation model. First of all, let's see what is a terminating system. Terminating systems are systems similar to a supermarket, a call center, a bank, CVS. All these scenarios, when we run the simulation, each day, system starts from zero entity in the system or a specific number of entity in the system. So at the start of the simulation every day, the system is in the same initial condition. In all these examples that I provided, we start with zero customer in the system. And then we continue running the simulation or running the system for a specific number of hours, 8 hours, 10 hours, 12 hours, for as long as you want to run. Then we stop the system. We do not let any new customer to come to the system. However, the system is going to continue running till everyone who is in the system gets the service and leaves, right? If we model, for example, a restaurant or a supermarket, maybe after 10 hours of operation, we close the door. We do not let any new customer to come in, but we still continue working for another half an hour, 20 minutes, or as long as it takes till everyone who is already in the store, who is already in the system, gets the service and leaves, and then we shut down for the day. Okay, so that's the definition of terminating system. So terminating systems are the ones that start from most of the time zero customer in the system or the same initial condition every time you run the simulation. And then they continue running for a specific number of hours. And then at that point, you do not want to let any new entity to enter the system. However, you want to continue running the simulation till as long as the entities that are already in the system get the service and leave. Okay, and examples that I gave you are a lot of real-world problems or real-world systems around us. The supermarket, the call center, the bank, the restaurant, a lot of the systems, especially in the service industry, follow that setup. So now we want to see how we can model such system, okay? The system that we are going to implement and learn this technique in is actually very simple, is a fast food. This fast food has an entry point that has capacity of 1 and then a waiting area that has capacity of 4. This queue has capacity of 4. So basically the whole waiting space has capacity of 5 for this fast food. If an entity comes and this area is full, there's 4 people in the waiting queue and there's 1 people in the entry point, then the customer gets rejected. It's not going to enter the system. Then the customers go to order food station to order the food, and then to make payment station, and then to pick up food station. And the processing time on each one of these stations is given to you in minutes. The customers arrive to the system every 6 minutes, exponentially distributed. And these are the things I know about this system. First of all, as I mentioned, if the waiting area is full, the customer is not going to enter it. It's going to be automatically rejected. The second thing is that the system, this fast food, is going to work for 8 hours. After the 8 hours of operation is done, they close the door. They do not let any new customer to enter. However, they continue working a little longer till every customer who is already in the system, all those people who are already in the queue or they are somewhere in these stations ordering the food or picking up the food, they continue working till all those customers that are already in the system get the service and leave, and then they close the door. And that's basically the end of the simulation for us. So we want to model this simple system and implement that terminating system condition rule. Okay. So I want you guys to please create a new model in the folder for week 7. We're going to name that model as fast food terminating system, and create these five locations. All of them have capacity of infinity except the waiting area or waiting queue that has capacity of 4. We have 1 entity that comes to the system, customer, interarrival time of 6 minutes, exponentially distributed. And and we do the processes together. So please create the entities, create the locations, create the entity, create the arrival. We do the processes together to take care of the whole terminating conditions of the system. Okay, so please do that really fast, and then we do the processes together. This is my system. I have an entry, a waiting area, order food payment, and pick up food. Waiting area, I consider the queue, first in, first out, and I put the length of 20. My entity is the customer. Customers arrive to the system, to the entry point one by one for as long as I run the simulation within the arrival time of 6 minutes. And now I want to take care of the processes. So the customer comes to the entry point. But right here at the entry point, I have to decide when the customer comes to, when the arrival is done, I have to decide, should the customer come in or not? What is the first condition I have to consider if the customer wants to come in or not, or if the customer can come in or not?
Are you guys full?
If I'm worried about the customers, the waiting area being full, the simulation will take care of that automatically. If there are people, 4 people in the waiting area and 1 people in entry already, when a new entity comes in, it automatically will be rejected. The entity will not come into the system. So yes, the being full is one condition. However, the system, the simulation, the pro model will take care of that automatically for us. When the waiting area is full, an entity is coming to the system, it will automatically get rejected and will not enter the system. What is the other condition I have to consider?
Are you guys open?
Are we open or not? Okay.
Yes,
So then I want to know for this customer if the customer has to come to the system or not. If we are open, the customer comes to the system and goes to waiting. And if we are not open, we are past the 8 hours of operation, the customer then goes to exit. We are not going to let the customer to come in, right? The customer gets to enter, but we are not going to let the customer to come in. We have passed the 8 hours, we are done. We are not going to come to our system. So we send the customer directly to exit from there. However, how should I tell the simulation that which one of these destinations the entity has to go to? Should you go to the waiting area or should you go to the exit? So we can specify that condition in the rule. So if I click on the first line and then the rule, here you see condition. Right here, I can specify and I can tell the simulation that when an entity comes to the system, gets to the entry, look at simulation time. If simulation time is less than or equal to 8, which means I'm in the first 8 hours of simulation, which means I'm in the 8 hours of working of the day, then let the customer to come in and let the customer go to the line and then order the food and so forth. So I want to write the condition here that when the customer comes in, check the simulation time. If the simulation time is less than 8, then let the customer comes in and goes to the waiting area. How can I write that? How can I get the simulation time? Clock is the command that is going to get the simulation time. And here I'm going to get the simulation time in hour. So I just write hour. Okay. But I don't need to use mod or anything like that because I just need the simulation time, plain. I need to get the simulation time, which clock hour is going to return the simulation time in hour for me. And I say when the simulation time is less than or equal to 8, that's my condition. Then let the customer to come in and go to this destination, which is let the customer go to the waiting area or stand in the queue. Okay. However, what is the condition under which the customer goes to exit? If clock in hour is greater than 8. If the simulation time has passed 8 hours of simulation, that means I'm past the 8 hours of operation in the day, then I don't want to let any new customer to come in, so the customer goes to exit. So that's the condition. So now let's assume the customer comes in. I'm in the first 8 hours of operation and the customer comes in. Then this is the customer. I'm going to pick the customer. The customer has come in. The customer has gone to the waiting area. Then the customer goes from waiting area to order food, from order food to payment, from payment to pickup, and from pickup to exit. And I know the processing times at order food 2, 1.5, and then 5. Okay, these are the processing times at order food, at payment, and pickup. Okay, so far I took care of the fact that if I'm past the 8 hours of operation, I'm not going to let any new customer to come in. Okay, now but remember we said we also want to stop at some point when every customer that is already in the system leaves the system. I want to stop at some point. So for now, let's just run the simulation with this setup. You see the simulation hour is just going to continue. Like I just wanted to run the simulation for a day, 8 hours, but simulation time is going to just continue, right? There is no stop condition for the simulation. So after 8 hours of operation, so what happens in this system is that after 8 hours of operation, simulation is not going to let any new customer to come in, send all of them to exit, but simulation just continue running forever. Customers come in, they don't come in, the customers come to the system, but they don't come in, they just go to exit. Customers come to the system, they don't come in, they go to the exit. That's all that happens after 8 hours. So I need to put that stop condition explicitly to just say that, okay, after 8 hours, do not let any new customer to come in. However, continue till everyone who is in the system gets the service and leaves, and then stop. And I want to implement that condition. So for that, all I need to do to check the stop condition is to make sure everyone who has come to the system has left the system. Once that happens, then I'm sure I have provided service to everyone who has entered the system. So all I need to do is to have a variable that counts how many people entered the system. I need a variable that counts how many people have left the system. And I need to check these two. And when these two are equal, I need to stop the simulation. Okay, so let's go then to the variables. I need to define two variables. One, to calculate how many people have arrived to the system. One, to calculate how many people are done and have left the system. And I need to check these two to see what is the right time to stop the simulation. Let's go to the variable and let's define these two variables. One for the arrive. I'm going to call it arrival. One for the arrival and one for processed. Both of them are integers because I'm just going to increase them by 1 when a customer arrives and when a customer leaves. And I'm going to use these two variables to check the stop condition, okay? So make sure to go to the variables, define these two variables, one arrival, one process, or give them any name that you want. Now let's go to the processing. I want to count number of people that enter the system. So I can start increasing the variable arrival right at the waiting area. When they finally get to the waiting area that they can go get the food, I can start increasing the variable arrival right there. That's where I can count how many people have come to the system. Where is the right place to count how many people have left the system or have been processed?
At the end, after E5.
Exactly, at the very end, then the last line. after we are done with the processing, after we are done with the wait operation, the wait comment, I'm going to increase processed to count how many people have received the service and they are done and obviously have left the system. Now I need to check these two and see when they are equal, meaning that everyone who has arrived to the system has left, and then stop the simulation right there. So let's go to the first line. I need to check these two and say that if arrival equals to the process, then stop the simulation. Now I want to ask you, can I write that condition here in the first line in the move logic, just to say, if number of people who have arrived to the system equals to number of number of people who have left the system, then stop the simulation. Can I do that? To just basically,
No.
let me just write the condition. If arrival equal processed, then stop. Stop, as you can see, is a blue word, is a keyword. When simulation sees this word, simulation just stops. So I say if arrival equals to process, then stop. And sorry, I have to write this at the move logic. So just for the sake of video, guys, I'm going to repeat this one more time. So here, in the first line, at the move logic, I'm going to write if arrival equal to processed, then stop. And here, as you can see, the stop is a blue word, is a keyword. So when the simulation sees this word, the simulation is going to stop automatically. So I wrote it here at the first line, that if number of people who have arrived to the system equals to number of people who have left the system, then stop the simulation. My question is this first line the right place to check this condition? Let's assume I'm in hour 3. And then this condition holds. Number of people who have arrived to the system equals to number of people who have been processed. So that's not the right time to stop the simulation, because I'm still in the working hour time. I'm still in the situation where the clock is less than 8 hours. While I'm in the working hour times, I don't care about number of people who came to the system is equal to the number of people who have left the system. Maybe I'm in just at noon, and yeah, by then all the people who have come to the system have left the system. Perfect. But I'm not going to stop the simulation then. I'm still in the working hours. So that's not the right time to check the stop condition. I'm still in the working hours. If I want to check the stop condition, I have to first let the 8 hours of simulation passes, let 8 hours of operation passes. So let's pass the 8 hours of operation, then check the stop condition, and then check if everyone who has come to the store has received the service and has left. And if that's the case, then I'm going to stop the simulation. And now let's run the simulation. You see, in my model, ran 8 hours and 19 minutes. That means after the 8 hours of simulation was done, 8 hours of operation, that means after 8 hours of operation was done, simulation is still needed to continue another 19 minutes for every entity who is already in the system gets the service and leaves, and then the simulation is stopped. I didn't specify any simulation runtime, nothing. All I did was to just run the simulation. Simulation ran for 8 hours and 19 minutes and then stopped based on the condition I put in the simulation in processes. Let's see the results. I have every 80 customers that have exited the system. My question is that, have all these 80 customers received the food and have left?
No.
Why?
Because you rejected customers when the waiting area is full, and then also after 8 hours.
Yes, I rejected customers when the waiting area was full. That's an exit. And also I rejected the customers after the 8 hours of operation. In that 19 extra minutes that we just saw that simulation ran, in that 19 extra minutes after 8, still customers were coming to the system, but they were directly, they directly went to the exit. I did not let them to come to the system because I was past the 8 hours of operation. So this total exit has more people than this total exit that we see here does not show exactly how many people we served. Okay, if I want to see how many people we served, where should I go? Or do I have anything in the model that can show me that? If I go to variables, then obviously here arrival and process is the same because everyone who arrived and left. But any one of these variables can show me how many people have received the food that got into the fast food, that got the food and they left the system. So I served 74 people in that 1 day of operation, which was 8 hours, 19 minutes in this system. That's the number of people that got the food, but these 80 people is number of people that left the system because they either got the food because they couldn't enter, system was full, so they left the system, or just because they came after 8 hours of operation. And they have spent about 20 minutes in the system to get the food and leave finally. Okay. Now, let's assume I asked you guys to, let's assume you have been hired by the manager of this restaurant and you're supposed to tell this person, on average, how many customers this restaurant is processing in a day? That's the question. How many customers we process in a day? What are you going to report?
74.
Okay. If I just report 74, that's equivalent to the situation that in the real world, I go stand by the door of the restaurant and just observe what happens in one specific day, let's say Monday. And I report that to the manager and say, oh, that's what happened. That's what I observed in Monday. So in a specific day, not in a, so on average in a day, you process or you receive 74 customers, or you process 74 customers. Is that number reliable? How about tomorrow? How about the next day? How about the weekends? If I just observe what happens in the restaurant in one day, that number is not going to really represent the number of customers that this restaurant can process in a day. That's just one day. How about other days? How about weekends? How about early in the week? So we need to come up with a better system to come up to represent a more reliable number that represents how many customers can get processed in this restaurant in a day. Okay. So now we want to see how we can do that. In the real world, if I was going to do that, I would just go stand by the door in more days to try to get sample of number of customers that have been processed in the restaurant in more days. I will go do it maybe in 30 days, month, throughout the whole week, in the weekends. I'll just go and stand by the door and count how many customers leave the system and just get more and more samples of number of customers that got processed in a day. Maybe after 30 days, I have, okay, now observations over 30 days. Now I can calculate the average across all these 30 days and say that, okay, on average, you process this number of customers in a day. That would be a more reliable number. Okay, that's what I would do in the real world. In the simulation, we can do similar things. The concept of replication that we have in the simulation options window help us to implement that idea. In the real world, you go get more samples. In the simulation world, we can just run the simulation for a couple of replications, for more replications. Each replication will be like a day, like a separate day for us. we start again the simulation from no customer in the system. We run till finally we are past the 8 hours of operations, and then we stop. And then we have the results for that replication. So we can just run simulation for more replications, and each replications will give us the results as if we are observing a separate day or another day in the real world. So for now, let's run the simulation for 5 replications. Let's pick the replication as 5. Let's run it for 5 replications. And you see here, I see number of replications, run 5 of 5. For example, in the last replication, the system had to work 8 hours, 28 minutes till finally everyone is out. Let's see the results. Here you see previously, maybe you guys didn't pay attention much, but previously when we would run the system, which always by default was 1 replication, here you would see replication 1. But now you see average. Let's see what is that. I want you guys to come here in the left, you see replications, and instead of average, pick all. Now here I see the result of all replications. So I have run the simulation for 5 replications. I see the result of all 5 replications separately. And you see each replication is like a different day, different set of random numbers that has been used for the arrival of customers and for processing of customers have led to different results. I have gone from anywhere like 70 customers in a day to 93. You see how these numbers are different? That's why I wasn't so concerned about sometimes your numbers were a little different from mine, because even in one computer with one setup, just running running the same simulation for different replication leads to different results just because we are using different random numbers. So we not only see the result of all replications, but you can also see their average as well. If I pick the average, it just removes the replication and just reports the average across all replications. Okay. However, I prefer to see all. One other area that I want you guys to go to, statistics, is also an important area where can report a lot of statistics related to these 5 replications. So I not only want to see the result of each replication separately, I want to also see their averages as well. And this time when I pick the average, it's not going to remove the replication. It keeps the replication and shows the average. I want to see the minimum across all the replications. I want to see maybe the maximum across all replications. I want to see the standard deviation across all replications. Okay. I'm going to uncheck min and max just for the sake of having this space. So for now, I show the average and standard deviation across all replications for everything that the simulation calculates, everything. And confidence interval is another thing that is calculated. And let's assume I want to show also a 95% confidence interval. So here, basically, the model says that on average, total exit during the simulation runtime was 79. The standard deviation is none. Obviously, every day is different. There is variability. The average is 79. The standard deviation is 9. And with 95% confidence, this average can vary between 68 and 91. Okay, I'll explain to you in a little bit what this confidence interval means and how we can use it. Now, let's assume I want to look at number of customers that have been processed in a day. Still, we want to answer that question that your manager asked. How many customers were processed in this restaurant in a day? This is total exit. This is not what I want. I want to look at number of customers that were processed. So I have to go to the variable. Right here, I'm going to also look at processed variable. Okay, I'm going to just not show the arrival just for the sake of not getting confused. I just want to look at the process. That's the one that shows me how many customers got processed in a day. They really came to the restaurant, got the food and left, not just the exit overall, but how the people who came to the restaurant got the food and left. I want to see, first of all, the result of all the replications. And as you can see, my numbers vary all the way from 68 to 93. Again, that's about 25 or so difference. So it's okay if our numbers in my simulation and yours are sometimes a little different, not too much. If you observe 20 people have left the system and I observe 93, that is a lot of difference. I would be concerned about that. But 70, 80, 90, that's a reasonable difference. So I want to see the result of all replications. I also want to see the average and standard deviation. And right now, then your boss asks you, tell me on average, tell me how many customers we process in a day. What number are you going to report?
The average.
The average. We are going to report the average. That's the number that we are going to report. We are going to say that on average, you process about 7 customers. I'm not going to say 93 because that's just representative of one day. I'm not going to say 70, that's just representative of one day. I'm going to say 77, which is average of number of customers that have left the system across 5 days. I'm going to report the average, okay? However, let's assume you have another colleague, another industrial engineer who is working for the company to improve the service. And that person also has been charged with the task of estimating how many customers we process in a day. And let's say that person has gone and has also observed what happens in this restaurant or in this fast food in 5 different days, in another 5 days. That person has collected data across 5 other days, and that person is also reporting the average across 5 other days. Do you think that average is the same as the ones that you come up with?
No, there's going to be a difference.
Then no, that's 5 different days. The number of customers who come and get the service in those 5 days are going to be different, the same way that your days are different. And that person is going to come up with a different average and is going to report a different average. Then the challenge of your manager here is, which one of these averages is correct? Should I trust your number or should I trust the other person's number? Okay, so that's the challenge that we want to address here. And for that, you have to let me to connect my iPad in a second. So our variable, our random variable, something that is variable, we don't know exactly the value, is number of customers processed in a day. Okay, in this fast food. And let's assume this number of customers that are processed in a day, obviously every day is different, this random variable has a distribution. Let's assume it has normal distribution with some average mu and some standard deviation sigma. Okay, so this random variable, this x, which is my random variable, has normal distribution with average mu and standard deviation x. So what does this mean? That means the number of customers that this store is processing in a day, obviously is different. Every day is different. That's why it is random. We don't know exactly how many people we are going to serve tomorrow. That's why it is random. We assume it has normal distribution. And there is some average, like we say, okay, on average, we process, I don't know, 75 customers in a day or so, okay? And also, this standard deviation is the measure of variability. Obviously, as we said, this is a random number, it's variable, it changes every day. So this standard deviation will be a measure of variability. So now, I don't know what is average number of people that this restaurant processes in a day? If I knew that number for a fact, I would just report it to my boss and I was done. I don't know that number. I don't know on average how many customers are processed in this restaurant in a day. I need to come up with that number. I need to estimate that number. What did I do? I took a sample. So if I had the power to run this restaurant for all the days in the world that this restaurant was going to work in, then I had the whole distribution and I could just look at the average of those numbers and report the mu. However, I don't have that luxury or that possibility. What do I do then? To come up with an estimate of the average of the number of customers that are processed in this restaurant in a day, what do I do then? We take a sample. Okay. I don't have the possibility to observe what happens in these restaurants in all the days, but I can take a sample and look at some of the days. I can take a sample of size n, and here's n is 5. We took a sample, we ran the simulation for 5 replications, or look at what happens in the restaurant in 5 days, or ran the simulation for 5 replications. So the sample size here is 5. And then look at the average across the sample. So in this sample, you look at the average. I'm going to look at the average across this sample. I'm going to show it by x bar 1. So across this sample, this is the average that we came up with. And I'm going to report that as an estimate for this unknown mu. However, the situation that we came up with was that your colleague is going to take another sample, okay, of size n as well, or a different size, it doesn't matter. And then that person is going to come up with a different number for the average across this second sample. Okay, so this is sample 1, the first sample, or I'm calling it the first sample. This is second sample. So your colleague comes up with a different average across this sample that he or she is going to get. And both of you have these numbers and then want to report these numbers, and then your boss is confused because these numbers are not the same. These numbers are different. So your boss is confused. Should I trust this number or should I trust this number? That's where the power of confidence interval comes in. So confidence interval. So with confidence interval, we basically take care of this situation. With confidence interval, we say that, okay, I took a sample. This is the average across my sample. However, I know that if I repeat this sample, if I take another sample of the same size or a different size, it doesn't matter. This average is going to be different. I know that. However, I expect these averages that you come up with in different samples to vary in this interval, to just be in this interval, to go from this lower bound to this upper bound. So that's why I'm also reporting a confidence interval in addition to the average of my sample. Just say that I took a sample of size n. This is the average across my sample, but I know this average is going to be different for different samples, for other samples that I may take, but I do not expect this average to go below this lower bound or to go above this upper bound with this confidence level. So those are the numbers. So those are the reasons why we report the confidence interval. So now let's see how these numbers are calculated in the model. So in your model, go to look at your results for the process. Can someone tell me, Victor, can you tell me for the processed number of customers that have been processed, what is the average you got across all the replications?
I got 77.2.
Okay. And what is the lower bound of your 95% confidence interval?
Lower bound is 64.62.
Okay. And upper bound?
89.78.
So I would say, okay, I observe what happens in this restaurant across 5 days. On average, I expect to get about 77 customers in a day. However, I expect this average to vary between 64 to 89 with 95% confidence. So you have 95% confidence that the average number of people that this restaurant is going to process in a day to fall somewhere between 64 to 89. Okay. Let's go back to our discussion here. Let's look at the formula that we have for the confidence interval. So, and why I want to continue the discussion here. First of all, everyone, okay, let me stop broadcast. Okay, everyone, please, okay, everyone, please go to your variable summary. I'm going to ask you guys to share your screen so that I see what you have got. You guys have done every step with me, so make sure you are you are following. Go to the variable summary, uncheck arrival, just because I don't want to have this page crowded. Get the process. I want you to show all the replications, average, standard deviation, and 95% confidence interval, okay? Then I'm going to export these results to an Excel file. And to be able to do that, I need to go to export, click on the chart file, chart data option, and here choose report. And here it asks you to save the file. You can keep the same name of the model and just save it in the same folder for week 7. Okay, so this is exactly what you were seeing in that table. It brought everything for you in that Excel file. So in this Excel file, what I want is the maximum. That's the column that I'm looking at, right? Delete every other column. Just keep the maximum. Okay, so keep the maximum. Okay, I have the replications average, standard deviation, a lower bound of the confidence interval and upper bound of the confidence interval. Average and lower bound and upper bound are the ones that I care about. Now, I want you to calculate the size of the confidence interval for me. What is the size of confidence interval? Upper bound minus lower bound. The length of the confidence interval. When we go from lower bound to upper bound, what is that length? I want you guys to pay attention to what we have here. Here I'm saying, on average, I expect 77 customers, but with 95% confidence, the average is going to vary between 64 to 89. And if your boss or your manager wants to use this number for planning for purposes to know how much meat they have to buy a day, then the person doesn't know like what number to use for planning. Okay, if I'm planning based on 77 customer, and then I end up getting 64 or 65 people, then I will end up with a lot of meat that I have bought because I expected 77 customers, but now at the end of the day, I cannot use those. Let's assume they are expired. So that's a lot of cost. Let's assume I plan for 77 customers, but that day you end up getting 89 customers or so. So then you have a lot of potential customers that are potential revenue, but you cannot provide service to them because you got prepared just for 77 customers, right? So what I see here is that this interval that I have is very wide. Yes, the average is 77, and I know this is going to vary between 64 to 89, but this is such a wide confidence interval. What if my number is not 77? What is 64? What if it's 89? These numbers are far from each other, and each one of them that I use for planning purposes can lead to completely different things. So we usually, if I'm going to estimate something, when I come up with an estimate value, which is this average, I want my confidence interval to be narrow so that I know, okay, this is the average, and the average is going to change between 75 to, let's say, 79. So, okay, if I'm planning is still for 77 and 75 people show up, not a big deal. If it's, so I'm planning for 77 and 79 people show up, not a big deal, okay? So when you are trying to estimate something and you report average and a confidence interval, we always love to have this interval as narrow as possible, because that helps us to make some confidence, to have some reliability in our average. If our confidence interval is so wide, I mean, then using this average is not helpful, because our numbers can be anywhere in this space. So we do want to come up with confidence interval that are narrow. Okay, so now we want to see how potentially, what are the changes we can make in this whole process to not only come up with an average, but also with the confidence interval that is narrow, so that I can build some confidence and I have some trust in the average that I can come up with, that I have come up with, and I can really use that for planning purposes. Okay, so that's what we want to do. Let's see what is the formula for confidence interval. So this is my average. I took a sample of size n. This is the average of the sample. For the upper bound, I get the average and I add something to it. And that's, if you remember from the statistics course, 3140, this is the number. This is what we add to the average to come up with the upper bound. So that's my upper bound. And from the average, I deduct something to come up with the lower bound. And that's the same amount to come up with the lower bound. Okay. So this is my average. This is my lower bound. This is my upper bound. And obviously, this is just average of the sample. This is the Z value that I get from the Z table. And we get that value based on the confidence level that we have. If I want to have 95% confidence interval, 99%, 90%, and so forth. This is the standard deviation of this random variable. For us, the random variable is number of customers we process in a day. So that's the standard deviation associated with that. And we assume that we know this. And the n is my sample size. This is the square root of n, and n is my sample size. Okay. So now, when I calculate this value and I add it to average, I come up with upper bound. And when I deduct the same value from the average, I come up with lower bound. If I want to have a narrower confidence interval, if I want to shrink the confidence interval, have a narrower confidence interval, I then have to make sure, I have to make sure that this value that I add to the confidence interval, I'm going to call it E. Okay, so this is E. I'm going to call this E. I have to make sure that this E is a small. If I have to make sure that the E is a small, then I know the upper bound is not going to go too far. And if I know that E is a small, the ones that I deduct from X bar to get the lower bound, if I know that the E is a small, then I know my lower bound is not going to go too far. Guys, please mute yourself. If I know that E is small, then I know that my upper bound is not going to go far, my lower bound is not going to go far, so my whole confidence interval is going to stay as a narrow confidence interval. So then the only thing I can play with is E. And I have to make sure that E is small. I have to make sure to bring the value of the E down as much as possible. So now help me with this. I want to bring the value of E down. This whole thing, I want to bring this value down. Z is something I get from the Z table, depends on the confidence level. I cannot change it. I cannot play with it. Z associated with 95% confidence is this value, and that's it. I cannot change that. Sigma is a standard deviation of this characteristic of this interest is not under my control. I cannot change that. The only thing that I can change in this formula is N. If anything, I can change N, which is the sample size. Can you tell me for the whole E to go down, to get smaller, what should I do with N? Should I increase it or decrease it?
Increase it.
I have to increase it because N is in the denominator here. N is in the denominator. You see a Z is Z multiplied by sigma divided by square root of N. N is in the denominator. So if I want to decrease this whole E, I have to increase N. That means I have to increase sample size. N is sample size, right? I have to increase sample size. Now, so basically what we came up with says that if you want to come up with a narrow confidence interval, increase the sample size. That way you come up with an average and a narrow confidence interval around the average, a lower bound and upper bound around the average. So this average is more reliable. Just because you took a larger sample. Intuitively, also this makes sense because when we take a larger sample, if you want to estimate something and you get a large sample that represent that thing, so then you're good. You're like, I have taken a lot of samples. If I look at average of these samples with a very good chance, I can get a good estimate of this characteristic of interest that I'm trying to estimate because my sample size is large. If you want to estimate, for example, the height of the people in the US, and you just pick 5 people and measure their height and just say, oh, average of the height of people in the US is this much. Would you have trust in that number? Or if you could take a sample of 100,000 people and look at the average of the height of 100,000 people. Obviously, when you get a large sample, you have a higher trust on that average that you get from that large sample as opposed to 2 people or 5 people, right? So in the statistics, the sampling literature, we always want to have big samples. If we can, we want to have large samples because that always gives us a good estimate of the characteristic of interest. And here the formula also recommends the same thing to us here. So now for this E that I just wrote here on the top, let's write down the E here one more time at the bottom. E is Z sigma over square root of N. And we just said we want to bring E down, and we learned that to be able to do that, I have to increase the N or my sample size. Okay, we just learned that. We just concluded that together. Now, if I tell you a desired E, and E, just to make sure, guys, E here is something that I added to average and I deducted from the average. So E is the size of the half of the confidence interval. Why? Okay, if I want to write down the size of the confidence interval, size of, or let's, instead of size, let me say length. Length would be a better word. Length of confidence interval. If I want to calculate the length of confidence interval is upper bound minus lower bound. Upper bound is x bar plus E. Lower bound is X bar minus E. So upper bound minus lower bound is going to return 2E. Okay, X bars cancel with each other. So what is left? It is 2E. So the length of confidence interval is 2E from the lower bound all the way to upper bound. So then size of half of the confidence interval is E. Okay, that's just a simple conclusion. So if the size of the whole confidence interval from lower bound to upper bound is 2E, size of the half of the confidence interval is E. Okay, so now if I tell you the value of the E, if I tell you that, you know, I don't want my confidence interval to be larger than, I don't know, the length of the confidence interval, I don't want it to be larger than 10. That means upper bound minus lower bound. Then you know automatically the size of the half of the confidence interval is going to be 5. 10 divided by 2, right? If I tell you that the size of the confidence interval, I don't want it to be above 10, then you know the size of the half of the confidence interval should not be above 5. So if E is given to you, given the fact that we know sigma is something that is fixed and Z is something that is fixed, we want to know what is the sample size that can give you this E that you want to have. So what is that sample size? So I can rewrite this formulation and find N. If I rewrite the same formulation, then N is going to be Z alpha over 2 sigma over E to the power of 2. Keep that important formulation. That's the formulation that can tell you what should be your sample size if you want the half of the size of the confidence interval to be E, which means you know already what you want to be the size of your confidence interval. So you know what is the half of the size of the half of the confidence interval. So you know, then you want to know what should be N that can give you that size of the confidence interval. And that's what we want to learn to do here, because a lot of the times we take a sample of size 5, we develop an average, we come up with a confidence interval, but the confidence interval is so wide that doesn't help us really much. I don't have trust in my average. So I want to be able to take more samples. I want to be able to come up with a narrower, more reliable confidence interval. And to be able to do that, I want to know how many samples I need to get, and we want to learn to calculate that. So keep this formula. I'm going to use this formula. So take a note of this formula somewhere. I'm going to use it in a little bit. In this formula, if I do not have the sigma, which is a standard deviation of this random variable, which is the case in our problem. I don't have a standard deviation of number of customers that are processed in a day in the restaurant. If I do not have the sigma, then I can replace it with S, which is the standard deviation in the sample that I took. The standard deviation between number of customers that were processed in the restaurant in a day in the sample of size 5. The standard deviation, I can put it there. And then instead of Z, I'm going to use T distribution with these two parameters that we need to be able to calculate T, N-1 and alpha over 2. And E is still in the denominator, raise it to the power of 2. That's going to give me N. Okay, so if I do not have sigma, I have to replace it with S, standard deviation of the sample. So this is sample, standard deviation. And then the whole formula changes to this. So to also take a note of this formula. We are going to use that. Okay, let's go back. Okay, this is my Excel file, right? And we calculate the size of the confidence interval. It's 25 units lower bound, upper bound minus lower bound, and let's assume that's wide. I don't want that. Let's assume I want to come up with a new size for confidence interval. I want to come up with a narrower confidence interval. And I want this new confidence interval to be maybe 70%, let's assume, of the original one. Oops. I want this new confidence interval to be 70% of the original size. So 0.7 multiplied by the original size. So that's what I want to be the size of the new confidence interval that I'm going to develop. I haven't done it yet. I just know I want this size for the confidence interval. So that's going to, so then my new confidence interval, the one that I want to come up with, is going to have a size about 17 points, okay? Then what is the E in this scenario? Then size of half of new confidence interval, or the E, or I'm going to call it new E that I want to come up with, is going to be the size of the confidence interval divided by 2, right? So if I have the new size for the confidence interval, the one that I want to come up with, then divided by 2 gives me the new size for the half of confidence interval, obviously. So I want the new E, the new half of the confidence interval, to be this number. And we just, the formula that, the last formula that I told you, if you look at the formula one more time, to be able to, what I want to do now is to find out what is N, what is the sample size, new sample size, new N. I want to know what is the new sample size. I already took a sample of size 5, and that gave me this confidence, this length for the confidence interval. I don't want that. I want to see what is the new sample size that I have to get to come up with this new size for the confidence interval, or this new size for the half of the confidence interval. I want to calculate N. Look at the formula that I just highlighted with pink. In that formula, to be able to calculate N, I need S, which is standard deviation of the sample. That's the one you calculated here. We have it. That's S. Standard deviation of the sample. These 5 samples that we got, this is their standard deviation. That's S. Okay, I'm going to write here. That's S. The other thing that I want is the T value. Okay, and to be able to calculate the T value, let me write it here. T value from T table. Okay, T value from T table. To get the T value from T table, I need 2 things. I need to know N minus 1, which is called as degree of freedom. If you remember from the statistics, degree of freedom, or N minus 1. And then I also need to know alpha over 2, which is calculated based on the confidence level. Here, in the original sample that we took a sample of size 5, right? So N is 5 minus 1, that is 4. So the original sample I took has size 5, right? 5 replications. So original sample has size 5. This is the standard deviation of that sample. So for the T value that I have to put in the formula, N minus 1 is 5 minus 1, that's 4. And then that also was a 95% confidence interval. So alpha is always 1 minus that confidence level. 1 minus 95, and then alpha over 2 is going to be 0.05, right? 1 minus 0.95. 0.05 divided by 2. So I have a 95% confidence level. 1 minus that confidence level is always gives me alpha. 1 minus 0.95 gives me alpha. And then what I need to be able to calculate T value from the T table is alpha over 2. So alpha over 2 is 0.05 divided by 2, and that's 0.025. Now let's go to the T table and see with degree of freedom of 4 and alpha over 2 of 0.025, what is the T value? If I go to the T table, here I have the T table. You see in the first column, DF, degree of freedom. That's what it stands for. Degree of freedom. My degree of freedom is 4, so I have to look at row 4. And then here the shaded area shows the area on the right side, which is alpha over 2 in our scenario. So our alpha over 2 is 0.025. So that's the column that I have to look for. So the row for degree of freedom of 4 and the column for 0.025, which is alpha over 2. So the T value is 2.77. Okay? So the T value is this 2.77. So then the T value that I need to use in the formula to calculate Ln is 2.77. Okay, I'm going also to make it orange. Okay, and this is my new E, the ones that I wanna come up with. Okay. With these 3 orange values, then the formula for the sample size, if you look at the formula that I highlighted with pink one more time, N is parentheses T value, which is here, multiplied by S, which is here, I have it here, standard deviation on the top, divided by E, which is the size, the new size for the half of confidence interval, the E that I want to get to. And this is the new E that I want to get to. Close parentheses to the power 2. That's the formula that I highlighted with pink, and I asked you guys to take a note. If I press OK, then that's the value for N. So that's my new N. That means your new sample size. So your new sample size is going to be 10 point something or 11, let's say. That's your new sample size. Remember, we learned that if I want to come up with a narrower confidence interval, if I want to go from size of a confidence interval or length of the confidence interval, which is 25 to 17, I have to increase the sample size. Sample size is already 5. I want to increase it. What is the new sample size? We just calculated that new sample size is 10 point something or 11. It doesn't hurt to run one more replication. So I'm going to run the simulation for 11 replications, and I expect that after that, I come up with a better estimate for that and a narrower confidence interval, which hopefully helps me to build more confidence on the average that I have come up with. So let's go back. Go ahead.
Can I see the code for your new N real quick?
It's T multiplied by S divided by E, and then the whole thing to the power of 2.
Oh, I didn't square it. Thank you.
So now let's go back to our simulation model and run the simulation for 11 replications and see what do we get for the average of number of people that were served in the restaurant and the new confidence interval. Go to simulation options, change number of replications to 11, run. Let's go to variable summary. Again, I'm going to look at number of customers processed, the ones that we provided food to. I'm not going to show arrival just for the sake of not having a crowded view. I'm going to show, first of all, I don't want to show all the replications, I mean, it doesn't hurt, let's show it. These are all 11 replications I have. You see the numbers go all the way from 66 to 93. And what I want to show is the average. Obviously, that's the number that I'm going to report. And it doesn't hurt to know a standard deviation. And I also want to know the 95% confidence interval. So I have the average, I have the lower bound, and I have the upper bound for the confidence interval. So now I say that on average, in this restaurant, we have about 75, 76 customers in a day that we provide service to. And obviously this number is going to vary. This is just an estimate. However, with 95% confidence, I expect this number to just vary between 70 to 81. To just go 5 units lower or higher, to vary between 70 to 81. So what is the new length for the confidence interval, guys? How do you calculate that?
Is it upper bound minus lower bound?
Yeah, the new length for the confidence interval is the new upper bound minus new lower bound. So 81 minus 70, if I calculate that, that's going to be something around 10 something or 11, let's say. So we came all the way from a confidence interval that has the length of 25 to an confidence interval that has the length of 11. So the average is 75 and can vary all the way between 70 to 81. This is a narrower confidence interval, a more reliable, and this is a more reliable average. So increasing the sample size, as we expected, improved our estimation. So now we have an estimation of that unknown average, and this estimation is more reliable than the previous one that we had. And that's it. Yeah, so why this concept, why all this discussion is important? Because in the whole statistics, forget about simulation. In the statistics, taking samples, if you want to estimate something, there is something that you don't know, you want to estimate. It's not that always we can just go ahead and take as many samples as we want. In a lot of situations, taking samples are costly. For example, if you are looking at the power or resistance of the tire of a car, you have to get those tires, put them under some condition and see finally when they are going to tear apart and then measure that resistance. So for every sample that you get, you are basically creating tear in a tire and that tire is not usable anymore. And that is a cost to the company because you are basically ruining one of the tires, right? So that's the cost. So I cannot just go and say, oh, get 1,000 sample to measure the resistance of the strength of the tires. I cannot, because that's 1,000 tire that I have to throw away, and that's the cost to the company. So finding what is the right sample size that can give us a reliable estimate of whatever unknown we are looking for is always an important question, is an important question in the statistics. And the same here. Right now, our simulation is small. You run it, it gives you the answer in a couple of seconds. It doesn't matter. You run it 11 replications or 100 replications. However, this is not always the case. In a lot of real world situations, our simulations models are big. Running them takes a lot of time. It uses a lot of computational power. So I cannot just go ahead and say, oh, run the 100 replication. It just takes time. And if you want to come up with estimates in a reasonable time and so forth, you have to come up with a reasonable number in terms of how many times you have to run that simulation, how many replications is needed to come up with a narrower confidence interval, and more importantly, to come up with the confidence interval that you want. If you know the size, how many replications or how many samples are needed to come up with that desired confidence interval. And that's why we go through all this discussion to find out what is the desired number of replication.